So, H. Any questions about, okay, what H represents? What does it mean? If it's positive H, negative H. We talked about the different ways that we can find it, which we learned in Unit 6. Now, S. Do we have confidence that we could, in our own words, tell someone else what S is? And what does it mean if a process has a positive or negative delta S? Also, do we recall when given thermodynamic values about specific substances? So before, we've worked with enthalpies of formation. Do we remember what those are? Now, absolute entropies. Something to recall and be so careful of. The units of entropy are joule per Kelvin mole, and the units for enthalpies of formation and enthalpies of reaction are kilojoules per mole. So be so careful. That is definitely an opportunity to make a misstep. Well, we're going to oscillate between the unit packet and the packet that I had on your desk when you came in. And there was also a reference of all the equations. Never have to memorize. They're always accessible. So I thought I would make it a different color so it would stand out for you. To set the stage for today, then, to address what I just said out loud. So taking a look at the packet that was on your desk, could we please go ahead and answer question 1? And this is a select all that apply. Select all that apply. Okay, we'll take 15 more seconds. Okay. First, what does favorable mean? Reagan.
It means the reaction will occur without an energy.
Perfect. Without us having to invest heat, electricity, any effort on our part. So processes that are favorable, we could call them or describe them with one term or two terms. Go. Excellent. Thermodynamically favored. Okay, so those and usually, you know, we're not required to have specific terms, but definitely. So thermodynamically favored, spontaneous. So what we want is exothermic and the change in entropy, Joey, to be positive or negative. You got it, you got it. So that's what we're looking for. That's it. So here's negative. Oh, negative. Nope. Negative, positive. Oh, yeah. Here's, no. Negative. Oh, there we go. And then, nope. That's it. Yeah. Okay. Now, there's a sometimes. There's a sometimes. Even when this is positive and this is negative. So the final check. I was wrong. I remembered after class. So, no. Mr. Hardy, not Big Daddy, Big Papa. That's what it was. So, what we referenced, this is final say. Final say about being thermodynamically favored. Ideally, we want negative delta G. Now, why? Because that means this is negative and then this is positive. So both things are working in our favor. If it's positive, then we have to invest that much energy. It's Gibbs free energy. So if it's negative, it's the amount of energy that is available to do work. If it's positive, that's the amount of energy we have to invest to do the work. If it's zero, we're not more favored in the forward than the reverse reaction. So we're at equilibrium. So when this is negative, we're favored to produce product. When this is positive, no, not so favored. We'd be favored in the opposite direction. And then here, nope, equal favorability, so equilibrium. Connor, what does that floating zero mean?
That's standard state.
Perfect. What are the values?
25, so it's 1/8 solution.
Excellent, excellent. So if we don't have that floating zero, and usually most circumstances lead us to that because we're not always beginning with 1 molar solution. So that honestly is how we would get there. But we'll most be working with these, of course. All right, questions? So this is the ideal situation. So these go together. I hope that makes sense. So we want a process to do its own thing. That's easier for us. That means it's thermodynamically favored. We can also use the term spontaneous when delta G is negative. This, it just means we have to do work. All right, so if we take a look at this reaction. Brendan, what does it mean if delta H is negative?
Exothermic.
Great. Delta S is positive? Yeah. Or we're increasing positional probability, the number of microstates. Yeah, very good. Well, this, we should definitely have a negative delta G, but let's find it. So if, delta G is, and I'm going to not put the not there because these aren't. Never have to memorize these. So if this is, Big Papa, this is the Big Papa equation. We just plug and chug. We have to be so careful though. Units. Delta H, delta G are usually kilojoules. So I would keep delta H in kilojoules and do the conversion of the delta S. Okay, easy peasy. So negative 196 kilojoules minus 298. And you don't have to show this. So 1,000 joules, 1 kilojoule. And we get negative 234 kilojoules, and it could be written kilojoules per mole reaction. if we would be asked, is this thermodynamically favored? We can say absolutely. If we have to justify, you can just say when delta G is negative, it's thermodynamically favored. We don't have to do any more explanation than that. We can make that association. Just like the temperature of a gas is directly related to its kinetic energy. We don't have to explain anything. Well, delta G being negative means thermodynamically favored. All right, so can you choose then which of these statements apply to this situation? Go. These aren't lettered or boxed, so we should have the first one, the second, the third, skip one, and then the fifth. Questions? All right, continuing onward. Oh, I love this question. Number 4. So, which of these is a thermodynamically favored reaction or process? Put an answer. We'll take 10 more seconds. All right, so we know these are what we're looking for. We should go right to this one and this one. Exothermic. That shouldn't even require much thought at all. Endo. Remember, reaction diagram. So if we end up at a higher potential energy, this is how much we have to invest. Nope. Those would be positive. So it's between these. Justin, how did you make the choice from there?
I said the last one because there's 1 mole of the product.
Not only that, we know if this is reaction progress, we're beginning with reactant and ending with product. We assume start and finish. So there's my reaction. And then here, oh, I think it's supposed to be C. I'm so sorry. Anyway. Yes. So we have 2 moles versus 1 mole. We know that the gaseous state is way more entropically favored. So many more positional probabilities, microstates, disorder. So we're going from a solid to 2 moles of gas. Here, we're making solid from gas. More order, and then less positional probability. Good? All right. Great question in number 5. All right, if we take a look, enthalpy, not for us, but entropy is. Hello, so good to see you today. You are welcome. We are looking at the packet that's on your desk. Okay, so it's asking, can we find what temperature we would need it to be spontaneous? Okay, what makes the final call? Delta G. How can we find delta G? A couple ways, but I would go to that equation first. These are not given floating zeros, so I'm not going to attach them. Well, here's temperature. And then I have my enthalpy of the process and my entropy of the process. I just need to solve for this. But I don't know delta G.
If you make it 0,
Why?
because then you can say like anything above whatever temperature you get, it'll make delta T negative.
To make this true, final word, excellent. We want delta G to be negative. Well, why don't we set this to be 0? We're looking at just the crossroads where if the temperature is greater, then that is going to make this term negative versus that. Excellent. Grace, excellent. Excellent. You need to be careful regarding our units. I'm going to go ahead and rearrange. So I'm going to add that term to both sides. So I'm not dealing with overtly negative. So 137 kilojoules per mole. I need to be careful. 121 joule per mole. Kelvin. Oh, they made an error. We're missing the Kelvin. But converting to kilojoules. And with sig figs, 1130 Kelvin. We're finding this not too shabby, especially given buffer problems. But a lot of times where we could get, we could make errors, like units, like just being careless about rearranging, misinterpreting signs. All right. So, ideally, we want this negative, this positive. That is always going to be thermodynamically favored. What will never be is if this is positive and that's negative. There's no way to make this negative. However, there are times when enthalpy could not be in our favor, but entropy is. And so if we conduct those at high temperatures, then we're making this term negative, hopefully more than that, and that'll deliver a negative delta G. Yeah? So it's asking here, which would not be favorable at low temperature, but would be at high. Take a look and we'll check. Good, more time. Alan, do you mind sharing what one? Could you share one that you did choose? So this positive, so this is thermodynamically in our favor. So if we run this at a very high temperature, hopefully this will be, it will be. Very good, very good. The third option, 2. So do we understand like why this is not good? Or, I mean, this would not be. So remember, this is in our favor. This isn't, but this would be 0.190 kilojoules. So in comparison, and we'll be multiplying by hundreds of Kelvin, but this is going to deliver us. Yeah, this is going to be thermodynamically favored. So even though this is in our favor, we can look at the magnitude of the delta H. And then here, yeah, look. So this is in our favor. Oh, and that's in our favor, so we don't even have to go down that path. But, you know, we're looking at, well, how much do we have to have the temperature if we're just comparing magnitude? Yeah. All right. Questions? Okay, moving right along. Okay. So we are vaporizing bromine. Remember, bromine is a halogen, it's diatomic, just like fluorine, chlorine, and iodine. Bromine under standard state is a gorgeous deep orange liquid. Toxic. So we would never want to be around it, especially to breathe in the vapors. So this is our process. We're just vaporizing, and we're asked to find the delta H naught and the delta. And look what we're given. The best math symbol ever. Remember, the enthalpy of formation of elements in their standard state. These equations will be given to you, so there's no excuse to not know that it's product minus reactant. And so officially, okay, the gas is our product. I totally get that, especially this one, like, do we have to show our work? No work, no credit. All right, so the delta H, 30.71. And remember, we could attach mole of reaction. Not that this is a chemical reaction, but a process. Now, Robert, does it make sense that for that vaporization, the enthalpy is positive? Because excellent, excellent, excellent. Not a chemical change. We're not breaking chemical bonds. We're breaking intermolecular forces. In fact, bromine, just as a reminder, non-polar. So it would just be one dispersion that we would have to overcome. All right. So, oh, I'm so sorry, Reagan. I missed what you said.
Oh, never mind.
Okay, thank you. So to get the entropy, now substances will always have an assigned entropy because only at absolute zero is the value 0. Okay, and we get for the entropy a value of 93. Now, officially then we've canceled moles, and so it'd be joule per Kelvin, but we could put joule per Kelvin mole reaction. And Joey, does it make sense that for this process, entropy is positive, the change in entropy?
It's going from liquid to gas.
Perfect, perfect, perfect. All right. At equilibrium, delta G is 0. When a pure substance is at its normal boiling point, equilibrium is achieved. Estimate the normal boiling point of Br2. When a substance, and so it's talking about boiling, not just average vaporization, it's an equilibrium that you're both vaporizing and condensing. You only know the direction if you know if heat is being invested or being released. And so if we say we know the phase change will happen at a position of equilibrium, again, it's kind of a way to try to find temperature, knowing delta H and delta S, and given the conditions. So when you plug and chug, be so careful about units. And we, trying to find V, of course. And the temperature that you should find is 330 Kelvin. Just an aside, remember, during a phase change, temperature does not change. So temperature would be constant while we're investing heat to overcome the intermolecular forces. Once we have all vapor, then we could increase the temperature. All righty, Rudy. So is this thermodynamically favored at 200 Kelvin? What is the best evidence? Going exactly, whatever you want to refer to this, Supreme Court, whoever I don't know, maybe your dad, your mom, whoever, I will say. All right. Yes, sir. Oh my gosh. I so much did, but yeah, it's the right answer. Thank you. Connor, thank you so much for finding my error. I'm sorry. Totally my fault. I was thinking of that. No excuse. No excuse. Thank you, Connor. Very, very much. All right. So Connor, thermodynamically favored at 200 Kelvin because?
It changes.
Excellent. That's it. That's all we have to say. Not thermodynamically favored or non-spontaneous because delta G. All right. king. Delta G, the Big Daddy, Big Papa, whatever Supreme Court justice. Capital K. And capital K, Colby, I know you know. You got it. Little side question. What is lowercase k? Yeah, thank you very, very much. Yeah. So in the rate law, don't worry, we will go over all this great stuff. Yeah. And this is impacted by temperature and activation energy, all that wonderful stuff. Only changes with temperature and reaction. All right. So the equilibrium constant. So, Amelia, if K is greater than 1, what do we know? Yep, products are favored. Overall, that is the perfect term to say, or perfect set of terms that we're product favored. We could pretty much say that we have a greater concentration of product compared to reactant, although it depends on the reaction, but product favored. And then if K is less than 1, it's reactant favored. If K equals 1, well, then we say we have pretty much the same amount of water. Remember that in both bins, but this is very, very rare, very rare. So how wonderful that we have an equation, and your book goes through how this was developed. We can just apply it. We can just apply it. Be careful because it's a natural log, not a log. So delta G, we know, is going to be kilojoules per mole reaction. We're taking the natural log of the rate constant that has no units on it. So this won't have a unit. Temperature, we've kind of seen, needs to be in Kelvin. So how do we get kilojoules? R. We've usually referred to this as the gas constant, but we might not have gases in our situation. So when we need joules or kilojoules, we will use the value of R. That's why I included it here. You will be given the value of R by me, by the College Board, by your collegiate professors. So we only use the 0.08206. PV equals nRT. Period. End of discussion. Done. Only with gases. Any other time, we're using this. Okay? But isn't this, Dylan, so annoying? Delta G is usually in kilojoules, but your R is in joules. So what are we going to have to do to be able to get kilojoules? Either convert before you do the math or convert afterwards. Okay. Jacob. If you kind of gotten like what we conclude from a negative delta G, what is that telling us? Perfect. So,
Product favorite.
So what would we predict the K value would be? Ah, brilliant, brilliant, brilliant. So we can check. But this would be what we predict. Yeah. So here's a reaction. Let's work through this and then break for homeroom. So we have this process. Sorry, they're not subscripted. Oh, we're given delta G. We know it's negative. Oh, and we're given the delta H. So if we do CER, right? Claim, evidence, reasoning. Although Mrs. Pinto shared that, I forget, she uses different letters in AP US history, but they use a C for the last, connect. Oh, I like that. Because that's what we seem to struggle with is the reasoning. How does the evidence connect with the claim? Well, maybe we should call it CEC. Claim, what's the answer? Or maybe AEC. Answer, evidence, connect the evidence to the answer. So will K be greater than, less than, or equal to 1? Jacob, take it away.
It'll be greater than 1.
Okay, what's the evidence? How do you know this? Yep. No, you could just say this, but sometimes I just like to say, like, you were given this. That's a Gerhardt thing. And so the reasoning is when delta G of the reaction, the process thermodynamically favored. Again, this is a Gerhardt in the forward direction. Thermodynamically favored, it's just assume you're talking about the forward direction. Therefore, will be product favored. Oh, Amelia, that was perfect wording. Therefore, K is greater than 1. All right. We'll come back and then solve for. If you have any questions during homeroom, please let me know.